Welcome. So in this video, I want to talk about IPv4 addressing. We're at layer 3, the network layer of the OSI model. We're going to be talking about IPv4 addressing, part of the IPv4 packet. Prior to this, my classes, we've talked about Ethernet. And Ethernet is really NIC card to NIC card, Ethernet NIC to Ethernet NIC, and not beyond the router. In IP, the IP header, we have source to destination address. This is original source, like PC3, to final destination. And I have here, it does not change. Now, little caveat to that. We'll talk about that in another video with NAT, network address translation. Let's just say in the real world, 99.9% of the time, from a client to a server and back, on the client side, excuse me, it has a private IPv4 address, and it does get NATed, translated to a public IPv4 address as it leaves the local router of that enterprise, that home, that resident, whatever, on its way to the ISP. But we'll talk about that another time. For now, let's keep it simple. The source and destination IPv4 addresses, for now, we'll just say do not change, but it's not an issue in this presentation anyway. So IP, Internet Protocol. It's more than just a source and destination IP address. It actually contains other information as well. In IPv4 here, we can see a whole bunch of information, but we're going to focus on just the source and destination address. We will be taking a look at IPv6 later. If you are watching this from the outside world at my classes, I have a whole playlist of IPv6 based on my second edition of my IPv6 book, if you wish to take a look at that. Okay, so IPv4 addresses, they are 32 bits. Okay, we represent them as dotted decimal notation. Each of these 8 bits we represent as a single decimal number in decimal. Okay. Boy, I got a little frog in my throat there. This provides about 4.29 billion addresses. Seemed like a lot at the time in the late 1970s when this was being developed, about the population of the Earth at the time. But as we'll talk about later, definitely not enough. Hasn't been enough for a long time, since the 1990s, actually. All right. Another video. That's when we get into network address translation and private IPv4 addresses. But for now, let's focus on the address itself. So that IPv4 addresses, 32 bits, but we write them in dotted decimal notation. So the way we do that is we divide the 32 bits into 4 8-bit bytes or octets. Then what we do is we convert each of the 8 bits to a binary number. Boy, that frog is just not leaving my throat. Oh, well. So the range of IPv4 addresses, if we were to write them out from all zeros to all ones, would be 0000 to 255, 255, 255. And we will see that the only decimal values that would ever use, because we represent this number in a format of using 8 bits, always be between 0 and 255. All right, let's take a look here. We have our little network that I've used in previous videos. Let's take a look at PC0 that has this IPv4 address and that subnet mask. Yeah, it's a prefix length. Let's take a look. Here's the IPv4 address, 192.168.1.100. And there's its subnet mask, 255, 255, 255.0. All right, if we write this out in both decimal, dotted decimal notation, and binary, we can see the 192.168.1.100. Okay, now, an IPv4 address is made up of actually 2 parts, a network portion, and that's the network that this device belongs to. We'll talk more about that in a moment. And we can see it's 192.168.1 in this example. and a host portion that uniquely identifies the device on that network, which is 100 in this example. Now, what determines what is the network portion of the address from the host portion? The subnet mask, also known as the prefix length. So every IPv4 address will also have a 32-bit subnet mask, also known as a prefix length. I'll talk more about that prefix length /24 in a moment. Okay, the subnet mask is what determines the network portion from the host portion of the address. A subnet mask is also 32 bits. It is a contiguous set of 1 bits, meaning all 1 bits, but once it changes to 0, the rest are all 0 bits. The 1 bits will identify or designate the network portion of our address. The 0 bits in the subnet mask will designate or identify the host portion of our address. So if you can see here, we have where the 1s end and the 0s begin, right? Okay, so if I move my line here, right where the 1s end and the 0s begin, where the 1s are in our network, which is a /24, that means we have 24 1 bits here. If I count the number of 1 bits, that's 24. That's how we get the prefix length. It used to be called also slash notation, but it's known as a prefix length. We can identify the subnet mask either way, 255, 255, 255, 0, or /24. Usually prefix length is a little easier. Okay, let's get back to this subnet mask. Where those 1s are, where the 1s end and 0s begin, where the 1s are, that's the network portion of our address. Where the 0s are, that identifies the host portion of our address. So we can see that where the 1s are here, that's the network portion of our address. Where the 0s are here, that's the host portion of our address. Okay, so if I was to do that up here, we can move that line right there. And 192.168.1 is the network portion. The 100 is the host portion on that network. Now, in case you're wondering, okay, the subnet mask I'm going to be showing you will be ending right in this presentation. Be on a what we call a natural octet boundary, here, here, or here. They do not have to be that way. We'll see that also in a moment, but let's continue for now. Let's take a look at another device on that same network, PC3, 192.168.1.103/24. Okay, so there it is. It's IPv4 address in dotted decimal notation and in binary. Okay, let's write out that same subnet mask, which is a /24. Okay, 255, 255, 255, 0. If I move this over again where the 1s end and the 0s begin, okay, there's our /24. Again, network portion is the 192.168.1, and the host is 103 on that network. Okay, so I move that over right there. Same network portion. That's not by coincidence as our other device. They're both on the 192.168.1. We'll see in a moment. It's here, 192.168.1.0 network. And it's 103 on that network. That's its unique host portion. The host portion needs to be unique. Let's take a look at another one. Our router, yes, our router actually belongs to this network. Actually belongs to 2 networks. As you can see, it belongs to this other network over here as well. Okay, but just like a host, it has an IPv4 address and subnet mask on that network. There's its IPv4 address in dotted decimal notation, subnet mask. Here it is in binary. Okay, there's the subnet mask. Let's put our little line there where the 1s and 0s begin. Again, same subnet mask, a /24 prefix length. There's our network portion. There's our host portion. Moving it up here. Okay, same network as our 2 hosts on that network. This is the local router. Yeah, sometimes I like to think of it as the local post office for those devices, those PC0 and PC3 that we took a look at. And it's the .1 host on that network. Okay, so if you look at all the devices here, all devices on the same IPv4 network must have the same subnet mask. Okay, so we could see our individual devices here. Here's the network address. We'll talk about that in a moment. Okay, it also is going to have the same network portion of our address. So all of these devices, same subnet mask, same network portion of their address. What's going to be different is the host portion of their address. That must be unique. You'll notice the network has a 0 in this example here for the network address, which it would have. All right. Also, they must be on the same side of the router. All right, over on the left here. Okay, again, same subnet mask /16. Same network portion. In this case, it's just 10.1. That's because of the subnet mask. The subnet mask is /16. I mean, it says just the first 16 bits, leftmost 16 bits, 10.1 identifies the network portion. Okay, we'll be talking more about that in a moment. Okay, they do have unique host portions of their address, which is the second two numbers, the second 16 bits. And you'll see our network address 00 in the host portion. And again, on the same side of the router. Okay. You can do whatever you want on a net. Beauty of networking is you can do whatever you want, but you're going to create problems for yourself. The worst kinds of problems are the ones that are intermittent. So if you start not playing by the rules, okay, then you're going to start having problems. Something Jeff Doyle is a guru in this industry, wrote the book called Routing TCP/IP and some other books. Anyway, look him up. Great guy, very knowledgeable. But one of the things he's always said is the protocols are there for you to abide by the rules. They're not there for you to challenge the protocol. Okay, so let's take a look at a network address. A network address, okay, here it is in decimal, here it is in binary. Let's take a look. A network address has all 0 bits in the host portion. So there's our prefix length, our subnet mask. We move this over. Let's take a look. There's the network portion, 192.168.1. Let's look at the host portion of that address. Notice there's all 0 bits in the host portion. Okay. All right. That means it's a network address. We cannot assign this address to a device. Okay. This is an address that represents the entire network. Okay. Talk about that more later. All right, move this over here. We can see here, there's the network portion. There's the host portion, all 0s in the network portion. So our network address, this is the address that represents all those devices, 192.168.1.101, 192.168.1.103, even the router's IP address, 192.168.1.1, all with /24 prefix lengths. They all belong to this network. 192.168.1.0/24. All right, let's talk about another address. This is known as a broadcast address. This is a special address that we would use when we want to send a packet to all devices. This is another address that cannot be assigned to a device on the network. Okay, so we'll talk more about that in a moment, but a broadcast address has all 1 bits in the host portion. All right, so let's move our line over. We have our 192.168.1 in the network portion. Notice in the host portion, we have all 1 bits. That gives us a broadcast address of 192.168.1.255. Okay. All 1 bits in the host portion. So if I move this over here, network portion, all 1 bits in the host portion. That's a broadcast address. All right, let's take a look at an example of a network with a /24 prefix length or subnet mask 255.255.255.0. That's actually what we've been looking at so far. Here's our network address, 192.168.1.0. We need to know the mask. okay? Because that's going to separate the network portion from the host portion. This address has all zeros in the host portion, all 0 bits in the host portion. Okay, we can see that right there. Here's our mask, okay, showing it in binary. Okay, all zeros in the host portion is our network address. Now we have 8 host bits. What does that mean? Well, the number of host bits tells us how many devices we can have in that network. So if we do 2 to the 8th, gives us 256. But remember, we just got done saying we cannot assign the network address to a device, and we cannot assign the broadcast address. We'll look at that in a moment, to a device. Everything in between, we can. So we actually have 254 available addresses to assign to end devices. Okay, the broadcast address is 192.168.255. Okay. All right. So again, so remember, devices live in a bubble. They don't see what we're seeing here. They only know their own addressing. Okay. So they know that they can reach any devices that are in the same network as themselves, but they don't really see each other. All they know is that their IPv4 address and subnet mask tells them that they are a member of the 192.168.1.0/24 network. That means they can encapsulate any packets to a device with a destination IP address that belongs to this network, 192.168.1.anything. Okay, we'll talk more about this in a moment, but they can encapsulate that in an Ethernet frame and send it from their NIC card to their NIC card directly, even the router's IP address. Okay, so let's look at what our host addresses are. Okay, we said our network address was a 0 in the host portion. Our broadcast address is a 255. So what are our valid host addresses? Well, the first host would be 192.168.1. Most commonly we assign that to the router. The last host address would be, well, 1 less than the broadcast. So you notice this is 1 more than the network address, and this is 1 less than the broadcast. This is our range of host addresses that we can assign. So any devices that have this IP address in the subnet mask know that they can reach each other directly from their NIC card to the NIC card of that other device. All right, so let's take a look at the network. Here we go. So this device here, 192.168.1.100. There's the network portion. There's its host portion. Okay, it knows. Let's move that over. Network portion, host on that network. Okay, it knows that it is a member of, well, all it's going to do is knows it's a member of a network. And all it's going to do is copy these network bits down here. Okay, it says that's my network portion. Oh, what network am I on? Well, this is my network portion of my address. My subnet mask tells me that. Okay, and the network I'm on, well, there's the network portion. I just put all 0 bits here, and I know that I'm a member of, put all 0 bits there, I'm a member of that network. This is how a device determines what network it belongs to. Every device does that. Every IPv4 device uses its IPv4 address and subnet mask. It's called a bitwise AND operation to determine what network it belongs to. Okay, so what this means is any devices that have an IP address, any packets it needs to send to a destination beginning with 192.168.1, it can reach it directly from its Ethernet NIC card to their Ethernet NIC card. Anything else in these 24 bits are different, can't get there directly. Got to forward those to the router. Okay, so let's take a look here. This device here, 192.168.1.100. Okay. Says, all right, there's my network portion, there's my host portion, doing that bitwise AND operation we just talked about. I'm on this network. Okay, this PC does the same thing. Okay, network portion, host portion of its address does that bitwise AND operation, putting all 0 bits in the network portion, says I belong to this network. they both realize that they are on the same network. All right. So the network address, all 0 bits in the host portion. Sometimes I think of it as like a family name or something. All right. So if we take a look at this, here's a network address, all 0 bits in the host portion. Here's our subnet mask. We take a look at the first host. All it is we copy the network bits. These blue bits are not going to change. All 0s and a 1 is our first host address. All 1s and a 0 is our last host address, converting them to decimal over here. All 1s is our broadcast. This works for any IP address and subnet mask. Okay, these rules apply to all IPv4 networks. Okay, here we have again, we have 8 bits in the host portion. We cannot assign the network address, this first one up here, to a device, cannot assign the broadcast to a device. This is the range of our hosts 1 to 254, 254 available addresses to assign to end devices. Okay, let's look at a different mask. What if it's 255, 255.00 or /16? Okay, notice, okay, 255, 255.00, our mask has changed. Okay, our 1 bits end here and our 0 bits start there. Okay, so the number of host bits you have, again, it determines how many devices you can have in your network. So how many host bits do we have here? Well, what I count are 16 bits. How many devices does that give you? -2, minus the network, minus the broadcast. 16 bits gives us 2 to the 16th, or 65,536 minus 2, or 65,534 addresses we can assign to end devices. That's how many end devices we could have in this network. All right, so what would be the first, last, and broadcast address? Very simple. Here's our network address. Here's our subnet mask. Put that line there. The network bits are not going to change. Okay, so let's copy it. Here's the network portion. All 0s and a 1 is our first host. All 1s and a 0 is our last host. I'm putting the addresses here. 192.168.0.1 is our first host. 192.168.255, 254 is our last host. And our broadcast would be 192.168.255, 255. Okay, this gives us 16 bits, 65,534 available addresses to assign to devices. Okay, so there's our network address, number of hosts, 65,000 plus devices. There's our broadcast. Okay, again, all of these devices, if they had this as their subnet mask /16, they would say, hey, I'm a member of the 192.168.0.0/16 network, meaning that they can reach any devices directly from NIC card to NIC card that have an IPv4 address starting only with 192.168. This is the host portion. Only the first 16 bits /16 is the network portion. All right, so what would be the first host? Well, there's our broadcast. Our network address is 00, broadcast 255, 255. Don't forget about the mask. The mask is important. That's what identifies the network portion from the host portion in any address. Here's our first host, 192.168.0.1. Last host, 192.168.255.254. Okay. All right. Now let's look at another one, 255.0.0.0 or /8. Wow, we're way over here. Look at all those host bits. Seeing that the mask is going to make a difference on how many end devices, how many addresses we have available to assign to end devices. 192.0.0.0. That's our network address. Our subnet mask 255.0.0.0. Subnet mask designates the network portion from the host portion. Okay, what's our first address? Let's just copy the network bits. It's only 8. This is a /8. copy the /8. Our first host is all zeros and a 1-bit, or 192.0.0.1. Our last host would be 192, the network portion, then all ones and a 0, or 192.255.255.254. The red bits are the host portion. And our broadcast, 192.255.255.255. Okay, this gives us 24 bits for end devices. Okay, that's how many available addresses we have. Look at this, 16,777,214. Again, we can't use the network address, can't use the broadcast address to assign to a device. All right, so there's our network address, subnet mask, that's 24 bits for our host broadcast address. Okay. I should probably put the /8 there so you know that it's only these 8 bits is the network portion. All right, so these devices say, hey, if I have a packet to send to another device and it just begins with 192 in the destination address, they're on my network. Okay. All right. So first, there's our broadcast. There I go. I put the subnet mask this time. 192.0.0.0 network address, broadcast 192.255.255.255 or /8. First host 192.0.0.1/8. Last host 192.255.255.254/8. Okay, so does the subnet mask determine how many end devices, hosts you can have on a network? Of course, yes, it does. If our subnet mask is a /24, 254 available addresses. Our subnet mask is a /16, and I'm telling you in prefix length here, but 255.255.0.0, 65,534 available addresses for end devices. It's a /8, 255.0.0.0, over 16 million. All right, so some questions here. Let's take a look at each one of these and let's see if we can determine what the network address is. This first one, 192.168.1.7 with this mask, put that line right there. Okay, 192.168 network portion, 00 would be the host. How about this one here? Look at the subnet mask. Okay, first 3 numbers in our subnet mask are 255. So the 10.5.10 is part of the network. 0, all 0 bits in the host portion would be the network address. Here we go. Notice same address, different mask. So in this case, if this was our mask, the network would be 10.0.0.0. Now here I've got 3 of the same IP addresses, but different masks. Let's see what their network would be. For number 18 here, 172.16.0.1/8. That means just the first 8 bits signifies the network. So the next 24 bits would be for our network address, be all 0 bits or 000 for the network address. How about here? Here we're saying just the first 16 bits identifies the network. So 172.16.0.0 would be the host portion, all 0 bits in the host portion, the network address. Now notice here, 172.16.0.1/24. So the first 24 bits, the first 3 decimal numbers they belong to the network. Only the last 8 bits, this last decimal number is the host. Notice the difference between these two. Okay, different mask. In this top one here, this 0 here, the 3rd decimal number, is part of the host. In this one here, because our mask is /24, this 0 here, this 3rd decimal number, belongs to the network. Okay, so it makes a difference what the mask is. That's why you have to know what the mask is. All right, again, all devices in the same network must have the same subnet mask or prefix length. They're going to have the same network portion of their address, but they are going to have a different host portion. and they'll be on the same side of the router. Okay, let's take a look at these two devices here. Let's say PC0 has a packet to send to PC3. So PC0 says, here's my IPv4 address. PC3, I'm sending a packet to its IPv4 address. Okay, can I reach it directly? I know my MAC address, but let's take a look. So it says, I know the network that I'm on is 192.168.1.0. It says, okay, I have all 0 bits in my host portion would be my network address. Now, when it looks at to determine the network address of the destination IP address, it does not know its subnet mask. Does not know its subnet mask. But it does know this. It says, hey, destination IPv4, 192.168.1.103. I know that if you were on my network, you would use the same mask as me. So I'm going to use my subnet mask on your IPv4 address. And if that gives me the same network as me, then we're on the same network. Yeah, okay, then you must be on my network. Okay. So it says, yes, we're on the same network. What does that mean down here? Well, PC0 says, I can look in my ARP table, look for your MAC address associated with this IP address, 192.168.1.103. If it's in there, I can put that in the destination MAC address and send this to you. If I don't know it, I'll send out an ARP request. You'll give me an ARP reply. I'll have your MAC address. I'll put in my ARP table for future reference, and I'll put it here, and I can send you this packet encapsulated in an Ethernet frame. Okay, how about this example here? Okay, PC0 sending to PCX. Source IP address, source MAC address of PC0, destination IP address 192.168.2.103. Again, PC0 already knows its network address. Okay. We saw that process earlier, and it knows I'm on the 192.168.1.0 network. When I put all zeros in the host portion, that would be my network address. I know that the first 24 bits identify the network portion of the address. So let me look at you, destination IPv4 address 192.168.2.103. I'm assuming that if we are on the same network, you better be using the same mask as me. So I'm going to use my mask here, 255.255.255.0. Okay, so I'm going to do that bitwise AND operation on your IPv4 address using my mask. Again, you're on my network, we're using the same mask. And let's see what it comes up with. Uh-oh, this doesn't look the same. 192.168.2.0. I put question marks here because I don't know your mask, but I do know this. We don't match. Okay, this does not match me, so you're not on my network. I'm not sure exactly what your network address is because I don't know your mask, but I know that we're not on the same network. So what does that mean? I can still send you packets. All I have to do is look in my ARP table of PC0 for the MAC address associated with my default gateway, my local router. If I don't know it, I'll send an ARP request. Hey, 192.168.1.1 in our example. Hey, what's your MAC address? It sends back a reply. Here's my MAC address and I can put that in my ARP table, put that here, and I can send the packet on its way. Okay. I'll be doing another video a little bit more on IPv4 that shows that the subnet masks do not have to end on dotted decimal, do not have to end on a natural octet boundary. That's what I wanted to say. Meaning they don't just have to be 255s and zeros. Okay, but we'll talk about that a little later. Hope this was a good refresher, review, introduction, however you use it for IPv4. Have a great day, everybody.